Guys, and welcome back to my channel. Long time no see. Guess who's back? Guess who's back? RLB is back. But we're not going over organic chemistry anymore. We are now on to biochemistry. Now, how this is going to work is going to be a little bit different than organic chemistry, okay? So basically, I'm going to explain concepts I really think you need to understand for the exam. You take some notes, you jot it down, you sit back, you relax, you drink some Red Bull, Gatorade, whatever you want to drink. Just listen to me explain these concepts and make sure you understand them for the exam, and I think you'll be A-okay. With that being said, let's start. Start by talking about Brownian motion. What is Brownian motion? Well, Brownian motion states that molecules move around in their environment due to random fluctuations in an environment's energy. So what does that mean in human terminology? Well, here I have a photo of pollen floating on water. And as we know, as temperature increases, water will begin to move around much more rapidly, or its entropy will also increase, meaning it's moving around much more randomly. Randomness is being increased once the entropy increases. And that increasing randomness and that increasing speed will actually cause the water to bounce around much more rapidly, making it more likely to hit these pollen grains, influencing the pollen grains' movement. Once again, that's Brownian motion, because Brownian motion states random changes in an environment's energy causes other molecules to move around in their environment. So that's the easiest way to think of Brownian motion. That little example I just gave you. Moving on, let's take a look at water. Now, I am not sponsored by Dasani, but I wish I was. But we're not talking about Dasani. We're actually talking about the chemical properties of water. So, water has a few properties that are super important to understand, especially for biochemistry, because a lot of the biochemical reactions revolve around water. Water is polar. Now, what the heck does that mean? Well, if you remember from Gen Chem 2, when you have an asymmetrical molecule that has a dipole moment, that's a polar molecule. But to simplify that for you, what I mean in this case is oxygen is partially negatively charged and the hydrogens are partially positively charged, which allows it to interact in its environment with other polar molecules. Now, we also need to know that polar dissolves polar and nonpolar dissolves nonpolar. Now, we're also going to dive into the hydrophobic effect here, because water drives the hydrophobic effect, and it's due to that polarity. This is why water drives that hydrophobic effect, and we're going to take a look at that on the next page. Now, here's the hydrophobic effect in action. So what exactly is the hydrophobic effect, you say? Well, polar molecules such as water like to bind to other polar molecules via hydrogen bonds. However, say we introduce a key villain into the equation, known as a nonpolar molecule. Think of it as the Green Goblin. Overall neutral molecule with no charge or dipole. That is your nonpolar molecule. The hydrophobic effect can then occur. Now then, what does the hydrophobic effect actually do, and why is it important for biochemistry? Well, it's a great organization tool for biochemistry. It can form protein, it can influence protein folding, it can also form cell membranes. Now, as you can see here, I actually have a little diagram drawn out of the hydrophobic effect. Now, we have the polar aqueous water surrounding the benzene rings that are in the middle. Now, the polar molecules are repelling the nonpolar molecules, because the nonpolar molecules are what we like to call hydrophobic. They hate water, so they're going to try and avoid them as much as possible, and that's going to drive them into the center of the aqueous solution. And then once they get driven into the center of this aqueous solution, they're going to start utilizing van der Waals forces in order to stabilize themselves with other nonpolar molecules, and that's going to drive them to be more organized. So basically, the concept to get away from here is, if you throw some nonpolar molecules such as benzene into a polar solution such as water, the nonpolar molecules are going to repel the polar molecules, and the polar molecules are going to repel the non-polar molecules, driving those nonpolar molecules into the center of the solution, where they will then interact with one another via van der Waals forces, forming them in a more organized manner. Now, also note that once they are in the center, the repulsion by these nonpolar molecules will cause the entropy of the polar molecules, the water, to increase. So that's what you really need to know. Now, moving on, let's dive a little deeper. Once again, I said polar molecules are hydrophilic. That means they're water-loving. So if you throw them in water, they're going to interact with the water. They're going to form hydrogen bonds, or they might form some electrostatic. They love to interact with water, mostly via hydrogen bonds. Non-polar molecules, they freaking hate water, man. They hate them. They're hydrophobic. They want to avoid them as much as possible. And once again, as I explained in the previous slide, they're just going to bunch up in the center and hide from the water. Now, majority of biochemical reactions occur in aqueous solutions, so these properties are very important to know. Now, examples, as I gave in the previous slide, is protein folding. The hydrophobic effect drives this event. And what do I mean by that? Well, you basically have hydrophilic amino residues on the outside of the protein that's folded, and you have hydrophobic nonpolar amino residues on the interior of these protein structures that are folded. So if you think of it this way, the red would be your hydrophilic, and the yellow would be your hydrophobic. And when this folds, it's going to cause the hydrophobic amino residues to be on the interior of the folded protein, and the polar hydrophilic amino residues to be on the exterior of the folded protein. So I'll write this here: exterior polar hydrophilic, interior nonpolar hydrophobic. Now, the same thing can occur in cell membrane formation. The inside of this molecule is going to be nonpolar. Those are going to be your hydrophobic tails. And the outside is going to be hydrophilic polar. Now, there's a special name given to a molecule that has two different chemical properties, and that's amphiphilic or amphoteric. You should definitely know that word. And amphiphilic, once again, means that it possesses two unique chemical properties, such as the molecule being polar and nonpolar at the same time, which is a great example of this would be this cell membrane here, since it's actually called a micelle. It has those hydrophilic heads and those hydrophobic tails, so nonpolar tails and polar heads, and it is an amphiphilic molecule. Once again, the hydrophobic effect drives that. So as you can see, the hydrophobic effect is really important. Now let's take a look at the different types of bonds that you're going to run across in biochemistry. So we all know what a covalent bond is: equally shared electrons between the bonds. So basically your pi bonds, your alkene bonds, alkyne bonds, all that good stuff. So these are your covalent bonds. You know, your basic organic chemistry structures, a majority of those are covalent bonds. Hydrogen bonds is more of a general chemistry concept. You probably don't understand that from organic chemistry. That's going to be more from Gen Chem. Now, hydrogen bonds drive a lot of biochemical reactions and form a lot of biochemical structures in biochemistry. They are very important bonds. They are weak bonds. And the thing you need to know about them is polar molecules utilize this bond. Nonpolar molecules do not utilize hydrogen bonds. So, if we have H2O and we are reacting them, and well, we have it, it's not reacting. If we have it in the vicinity of nitrogen, oxygen, and fluorine, which one's it going to bind to? Well, it can bind to all of them. They're all polar, and they all have a slight negative charge on them. However, if you take a look at this chart up here, know that fluorine forms a stronger hydrogen bond than oxygen, and oxygen forms a stronger hydrogen bond than nitrogen. Let's ignore fluorine, though, because fluorine doesn't really occur in biochemical reactions very often. So if you have an H2O molecule in the vicinity of a nitrogen and an oxygen, the oxygen's actually going to outcompete that nitrogen and steal the hydrogen bonding from the nitrogen, and nitrogen's going to go and cry. It's just, it lost. Go cry, nitrogen. Oxygen wins. Oxygen forms a stronger hydrogen bond. Beats out for the hydrogen bond with that oxygen molecule. Now, an important biochemical concept to relate this to is the DNA double helix. The DNA double helix is actually stabilized via hydrogen bonds between adenine, thymine, guanine, cytosine, all that good stuff. So basically, when thymine and adenine bind to each other in the double helix, they form hydrogen bonds between one another. And when guanine and cytosine bind with one another, they also bind via these hydrogen bonds, and that's actually what stabilizes the double helix structure. And why is this actually important? Well, we need to actually be able to access our genomic material in order to replicate our genes and all that good stuff. So these hydrogen bonds can be much more easily broken and also much more easily formed than a covalent bond. So for some reason, via evolution, we developed the hydrogen bond in order to bind our double helix together. And once again, it serves as a great resource because it can be easily broken, allowing for our genomic material to be utilized, while also stabilizing the structure. Van der Waals forces. Now these aren't, this is not a bond. This is an interaction, I like to call it. So think of this as not shaking your friend's hand, but more or less saluting your friend. That's basically what a Van der Waals force is. Now the fancy term of Van der Waals force is transient asymmetry in electrical charge. Now what does that actually mean? Because let's be honest here, transient asymmetry in electrical charge doesn't really make sense to many people. But to simplify that for you, if you have two neutral or nonpolar molecules, because neutral and nonpolar molecules utilize this force, polar molecules don't utilize Van der Waals forces, you will have these two molecules that when they get close to one another, they will actually cause an induced dipole moment. Now, what does that mean? Let me draw this out for you. Now, an induced dipole moment means that this nucleus in this atom will actually attract the electrons in this atom. They're both nonpolar, neutrally charged, and it will actually attract them, inducing a dipole moment, making this side of the atom partially positively charged and this side partially negatively charged. And basically, how to think of this is the closer they get, the more likely they are to attract to one another due to this asymmetry in the electron charge. I like to think of it as electron distribution, because the closer they get to one another, the electrons start moving more towards the nucleus of the other atom, inducing a dipole moment in the alternate atom. So basically, think of it this way. You have two neutral atoms. As they close in on one another, the nucleus of this atom, or they could be the other atom, it doesn't really matter, they're both neutrally charged, will attract the electrons in this atom, making an induced dipole moment, meaning that one side of this atom, this side, is now partially positively charged, and this side of the molecule is now partially negatively charged, and they are now attracted to one another. However, as they do increase in, the closer they do become to one another, this force will increase. However, once they get too close to one another, they'll actually repel one another again. There's like there's a maximum distance they can reach, and then they'll once again just repel each other because it'll realize that all along this molecule right here was catfishing this molecule. That's the best way to think of it. So basically, you have two neutrally charged nonpolar molecules that technically wouldn't want to be attracted to one another, because negatives and positives, if they're both neutral, there's nothing attracting to one another. Positive attracts negative, negative attracts positive. That's the key concept. But due to this Van der Waals force, the closer they get to one another, they can cause asymmetrical distribution of the electrons in the atom, which then will induce a dipole moment in the one atom, causing them to be slightly attracted to one another via this Van der Waals force. Moving on to the electrostatic interactions, also known as ionic bonds. Now, Pikachu loves these bonds, so let's take a look at the most generic ionic bond out there. That would be sodium chloride. You have a positively charged sodium and a negatively charged chlorine, which are ionically bound to one another. Another example of this would be the molecule I have drawn right here. Now, you'd think this would maybe want to react with one another and form a covalent bond. However, that's just not true, because you can't have 4 bonds on oxygen. It is physically impossible in the chemical reality. So what would happen here is an electrostatic interaction would occur, you can think of it as an ionic bond would occur. And basically what's happening is the positively charged oxygen is going to attract the negatively charged chlorine atom. However, they're not going to actually form a bond. They're basically just going to be attracted to one another and chill. But it's still technically considered a bond. And those are your electrostatic interactions. Now, a law that's super duper important with this concept is Coulomb's law. Now, Coulomb's law is utilized in order to determine the energy of these electrostatic interactions in ionic bonds. And Coulomb's law states that energy equals the proportionality constant times charge 1 times charge 2, divided by the dielectric constant times the distance. Now, one thing to know about the dielectric constant. When you are in water, it equals 80, and when you are in a vacuum, it equals 1. So, let's think of this conceptually, because this is going to be a big portion of the exam. He even said it in class. If you're in water, is the energy of this bond going to go up, or is the energy of this bond going to go down? Well, if D goes up because it's going to turn into 80 instead of 1, the energy would go down. If the denominator gets bigger, the overall value has to go down. Bigger the denominator, smaller the energy. Now then, let's take a look at something else. You're really not going to have to solve these problems. You just have to understand the concepts behind these problems. He's not going to actually give you a problem saying, "Oh, solve Coulomb's law." That's a physics problem. This is chemistry class. You just need to understand the concepts behind the equation. So we now understand how D influences energy. Let's now take a look at how distance R influences the energy of the bond. As we increase the distance, what happens to energy? Well, the denominator increases in size, so energy, once again, has to go down. That, once again, remember, this is if the top's staying constant, so keep that in mind. So the energy would have to go down if distance increases. If distance decreases, energy would actually increase because, once again, the denominator is getting smaller, so energy is increasing if distance decreases. Now then, let's take a look at the top of this equation. We have charge. This stays constant, so ignore K. K is always 8.9 times 10 to the 9th. I want to say it's measured in coulombs. I forget. It's a physics 2 equation, but don't even worry about that. But looking at charge 1 and charge 2, if the charges increase in size, energy increases in size. If the charges decrease in size, energy decreases in size. And that's basically all you have to know about that equation. You don't actually have to know how to solve it. Just understand basic mathematics and what each what each letter / variable actually represents here. Sorry about that, I had a brain fart. But yeah, and that's basically what you need to know for that. So on the next episode, we're going to take a quick look at pH. But with that being said, I hope you guys have a wonderful night and